Before we begin, a note about this episode. More than other episodes, it assumes knowledge of the subject matter during the conversation. So, although we'll repeat some basic definitions, before listening, there's a good chance you'll want to watch or read something explaining the mathematics of finite factored sets. The description of this episode will contain links to resources that I think do this well. Now, on to the interview. Hello, everybody. Today, I'll be speaking with Scott Garrabrant. Scott is a researcher at the Machine Intelligence Research Institute, or MIRI for short, and prior to that, he earned his PhD in mathematics at UCLA, studying combinatorics. Today, we'll be talking about his work on finite factored sets. For links to items that we'll be discussing, you can check the description of this episode, and you can read a transcript at axrp.net. Scott, welcome to Axrp. I guess we're going to start off talking about the finite factored sets work. But to start off that starting off, you've kind of compared this to, or I think it's sort of meant to be somehow in the same vein of G.A. Pearl's work on causality, where you have this like directed acyclic graph of nodes and arrows, and the nodes are like things that might happen, and the arrows are like one thing causing another kind of. So I'm wondering like, what's good about Pearlian causality? Like, why does it deserve to be developed on? Let's just start with that. What's good about Pearlian causality?
What's good about Pearlian causality? So specifically, I want to draw attention to the fact that I'm talking about kind of earlier Pearlian stuff. Like Pearl has a bunch of stuff. I'm talking about the stuff that you'll find in chapter 2 of the book Causality specifically. And I mean, so basically, it's a framework that allows you to take statistical data and from it infer temporal structure on the variables that you have, which is just really useful for a lot of concepts. There are a lot of purposes. It's a framework that allows you to kind of just go from pure probabilities to having an actual structure as to what's going on, and causality, which then lets you answer some questions about interventions possibly and things like that.
So if it's so great, why do we need to do any more work? Why can't we just all read his book and go home?
So my main issue is kind of a failure to work well with abstraction. And so we have these situations, possibly like coming from decision theory, where we want to model agents that are making some choice and they like have some effect on the world. And it makes sense to model these kind of things with causality, which is not like directly using like Pearlian causal inference, but like using just like kind of the general framework of causality, where we kind of draw these DAGs that draw these directed acyclic graphs with arrows that kind of represent effects that are happening. And you run into these problems where if you have an agent and, for example, it's being simulated by another agent, then there's this desire to put multiple different copies of the same structure in multiple different places in your causal story. And to me, it feels like this is really pointing towards needing the ability to have some of your nodes, some of your variables in your causal diagrams be abstract copies of other nodes and variables. And there's an issue, like the Pearlian paradigm doesn't really work well with being able to have some of your variables be abstract copies of others.
So what's an example of a place where you'd want to have like multiple copies of the same structure in different places? If you could spell that out.
Yeah, I can give like more specific, direct examples that kind of are made up examples, but really I want to claim that you can see a little bit of this anytime you have any agent that's making a decision. Agents will make decisions based on their model of the world, and then they'll make that decision, or based on the model of the consequences of their actions, and they'll make a decision and they'll take an action, and then those consequences of their action will actually take place in the real world. And so you can kind of see that there's like the agent's model of what will happen that is kind of causing the agent's choice, which kind of causes what actually happens. And there's this weird relationship between the agent's model of what will happen and what actually happens that could be well described as the agent's model is kind of an abstract version of the actual future.
Okay. And why can't we have abstractions in Pearlian causality?
Yeah. So the problem I think lies with what happens when you have some variables that are kind of deterministic functions of others. And so if you have a abstract refined version, or if you have a like refined version of a variable, and then you have another coarse abstract version of the same variable, you can kind of view the coarse version that has less detail as a deterministic function of the more refined variable. And then Perl has some stuff that like allows for determinism in the structure, but the part that I'm like that I really like doesn't really have a space for having some of your variables be deterministically or partially deterministically related.
Okay.
And in the parts of Perl where some of your variables can be deterministically related, the ability to do inference is much worse. The ability to infer causality from the statistical data.
Yeah. I guess, like, how, to what degree are we dealing with strict determinism here? Because, like, guesses can sometimes be wrong, right? If I'm thinking about the necessity of abstraction here, as like I have models about things, like it's not really the case that my model is like a deterministic function of reality, right?
Yeah, this is right. I mean, there's a story where you kind of can have some like real deterministic functions where you have like multiple copies of the same algorithm in different places in space time or something. But yeah, I feel like I'm kind of dancing around like my true crux with the Pearlian paradigm, and I don't know. I'm not very good at like actually pointing at this thing, but my true crux feels something like variable non-realism, where in the Pearlian world we have like all of these different variables, and you have a structure that kind of looks like this variable listens to this variable, and then this variable listens to this other variable to kind of determine what happens. And in my world, I'm kind of saying that, or I'm kind of in an ontology in which there's nothing real about the variables beyond their information content. And so if you had two variables, one of which is a copy of the other, it wouldn't really make sense to talk about like, yeah, if x and x prime were copies of each other, it wouldn't really make sense to ask is y looking at x or looking at x prime if they're actually the same information content. And so kind of philosophically, I think that like the biggest difference between my framework and Pearl's framework is something about denying the realism of the variables. Uh, yeah, that didn't really answer your question about do we really get determinism. Um, I mean, I think that systems that have a lot of determinism are useful for models. Like we also like we have systems that don't have real determinism, but we also don't actually analyze our systems in full detail. And so I can have a high level model of the situation, and while like this calculator is not actually deterministically related to this other calculator, like relative to my high level model, it kind of is. And so even if we like don't get real determinism in the real world, in high level models, it feels still useful to be able to work okay with determinism. But I don't know. I think that I don't know. In some sense, I want to say determinism is kind of the real crux, but in another sense, I want to say that it's distracting from the real crux. I'm not really sure.
It also seems like one issue. Let's say I'm playing Go and I'm thinking about what's going to happen when I make some move, and then I play the move, and then that thing happens. Well, if we say like that my model of what's happening is an abstraction of what actually happens, it's like a function of what actually happens, then it's the case that there's sort of an arrow from what actually happens to what I think is going to happen. And then there's an arrow from that to what I do. Because I that's what causes me to make the decision, and then like there's an arrow from like what I do to what actually happens because that's how normal things work. But then you have a loop, which you're sort of not allowed to have in Pearl's framework. So that seems like kind of a problem.
Yeah, I think that largely my general or a large part of my research motivation for the last I'm not sure how long, I think at least 3 years, has been a lot towards trying to fix this problem where you have a loop. Like thinking about decision theory and ways that like people were talking about decision theory in like I don't know around 2016 or something. There was like stuff that involved like well what happens when you take DAGs but you have loops and stuff like this. And I had this like glimmer of hope around well maybe we can not have loops when I realized that in a lot of stories like this the loop is kind of caused by wanting to have, like, by conflating a variable with an abstract copy of the same variable. And that's not what you did. What you did was you drew an arrow from the thing that actually happens to the to your model. And I think that, so in my framework, there aren't going to be arrows, but to the extent that there are arrows like this, it makes more sense to draw the arrow from the course model to what actually happens. And to the extent that the course model is like a noisy approximation of what actually happens, you kind of won't actually get an arrow there or something. But in my world, kind of the coarser descriptions of what's going on will kind of necessarily be no later than a more refined picture of the same thing. And so I think that I more want to say you don't want to draw that same kind of arrow between the real world and the model. And kind of, if I really wanted to like do all this with graphs, I would say you should at least draw like an undirected arrow that's kind of representing their logical entanglement that's not really causal or something like that. That's not the approach that I take. The approach that I take is to kind of throw all the graphs away. But yeah, so I largely like gained some hope that these weird situations that felt like they were happening all over the place in setting up decision theory problems and agents that trust themselves and think about themselves and do all sorts of reasoning about themselves. I gained some hope that all of the weird loopy stuff that's going on there might be able to be made less loopy via somehow combining temporal reasoning with abstraction. And that's largely a good description of a lot of what I've been working on for many years.
All right. I guess if I think concretely about this, like, course versus abstract thing, imagine I'm like, so basically think about the Newcomb scenario. So Newcomb's problem is like, there's this really smart agent called Omega, and Omega is simulating me, Daniel Phylan. And Omega gives me the choice to just like take one box that has an unknown amount of money to me in it, unknown to me, and two boxes where I take the unknown amount of money and also like a box that contains like $1,000, and I can just see that it definitely has $1,000. And Omega is like a weird type of agent that says, I figured out what you would do, and if you would have taken one box, I put a lot of money in the one box, but if you would have taken both, then I put almost none in it, and then I take one or the other. So what should I think of? It seems like in your story, there's an abstract variable, maybe in a non-realistic kind of way, because we're variable non-realists, but there's some kind of abstract variable that's like Omega's prediction of what I do, and then there's like what I actually do. And like if it's the case that Omega just correctly guesses, like always correctly predicts whether I'm going to one box or two box, what should I think of? Like in what way is this abstraction lossy, or what like extra information is there when I actually take the one or the two?
So I guess if Omega is just like completely predicting you correctly, then I don't want to say that like I kind of want to say, well, there's a variable-ish thing that is what you do, and it goes into Omega filling the boxes, and it also goes into you choosing the boxes, and it's kind of at one point in logical time or something like that. I think that the need for actual abstraction can be seen more in a situation where you, Daniel, can also partially simulate Omega and learn some facts about what Omega is going to predict about you. So maybe Omega is doing some stuff to predict you, and you're also simulating Omega. And in your simulation of Omega, you can see predictions about stuff that you're currently doing or about to do and stuff like that. And then there's this weird thing where now you have these weird loops between your action and your action. So in the situation where like Omega was kind of opaque to you, the intuition goes against what we normally think of as time, but we didn't necessarily get loops. But in the intuition where you're able to kind of see Omega's prediction of you, things are kind of necessarily lossy because you could kind of diagonalize against predictions of you, and kind of because it doesn't fit inside you. So let's see. if you're looking at a prediction of yourself and you have some like program trace, which is your like computation, and you're working with an object that is a prediction of yourself, and maybe it's a very good prediction of yourself, you're not actually going to be able to fully simulate every little part of the program trace because it's kind of contained inside your program trace. And so there's a sense in which I want to say there's some abstract facts that maybe are predictions or proofs about what Daniel will do. And that can kind of live inside Daniel's computation. And then Daniel's actual program trace is this more refined picture of the same thing. And so, yeah, I think the need for like actually having different levels of abstraction that are at different times is coming more from situations that are kind of actually loopy, as opposed to in the Newcomb problem you described, the only reason that it feels loopy is because we have this logical time and then we also have physical time. They seem to go in different directions.
So now we've gotten a bit into the motivation. What is a finite factored set?
Yeah, okay. So there's this thing, I don't know, I guess I first want to like recall the definition of a partition of a set. So a partition of a set is a set of subsets of that set. So we'll start with an original set S, and we'll have a partition of S is a set of subsets of S such that each of the sets is non-empty, and the sets are pairwise disjoint, so they don't have any common intersection. And when you union all the sets together, you get your original set S. So it's kind of a way to take your set and view it as a disjoint union.
Yeah, I kind of think of it as like dividing up a set into parts, and that way of dividing it up is a partition.
Yeah. And so I introduced this concept called a factorization, which can be thought of as a multiplicative version of a partition, where you kind of, in the partition story, you kind of put the sets next to each other and you kind of union them together to get the whole thing. And in a factorization, I instead want to kind of multiply your different sets together. And so the way I define a factorization of a set S is it's a set of non-trivial partitions of S such that for each way of choosing a single part from each of these partitions, there will be a unique element of S that's in the intersection of those parts. And so the same way that you can view partition as a disjoint union, you can view a factorization as a partition is a way to view S as a disjoint union. A factorization of S is a way to view S as a product.
Okay. And so to make that concrete, an example that I like to have in my head is suppose we have like points on a 2D plane, and we imagine the points have an x coordinate and a y coordinate. So one partition of the plane is I can divide the plane up into like, sets where the x coordinate is 0, sets where the x coordinate is 1, sets where the x coordinate is 2, and those look like lines that are sort of perpendicular to the x axis. And like none of those lines intersect, and every point has some x coordinate. So it's this set of lines that together cover the plane. That's one partitioning, the x partitioning. And there's another one for values of y, right, which look like horizontal lines that are various amounts up or down. And so once you have like the x partitioning and the y partitioning, like any point on the plane can be kind of uniquely identified by which part of the x partitioning it is and which part of the y partitioning it is, because it just tells you, how much to the right of the origin are you, how much above the origin are you. That just like picks out a single point. I'm wondering, like, do you think that's like a good kind of intuition to have?
Yeah, I think that's a great example. To say a little bit more there, so your original set S in that example you just gave is going to be the entire Cartesian plane, the set of all ordered pairs, like x coordinate comma y coordinate. And then your factorization is going to be a set B, which is going to have just two elements, and the two elements are the partition according to what is the y coordinate, and the partition according to what is the x coordinate. You can kind of view partitions as like questions, and so in general, if I have a set like the Cartesian plane and I want to specify a partition, one quick way to do that is I can just ask a question. I can say, what is the x coordinate? And that question kind of corresponds to the partition that breaks things up according to their x coordinate.
Okay. And the one slightly misleading thing about that example is that there are an infinite number of points in the xy plane, but of course we're talking about finite factored sets. So S only has a finite number of points.
Yeah, so we're talking about finite factored sets. So in general, I'll want to work with a pair S comma B, where S is a set, a finite set, and B is a factorization of S.
Why choose the letter B for a factorization?
It's for basis.
Mm.
Yeah, it's for basis. I largely, while I'm thinking of the elements of B as partitions of S, I'm also kind of just thinking of them as elements just out on their own that are kind of representing the different basis elements. Yeah, so it actually looks a lot like a basis because for any point in S, you can kind of uniquely specify it by specifying its kind of value on each of the basis partitions.
Okay. So, yeah, this gets into a question I have, which is how should I think about the factors here? Like these finite factored sets, I guess they're supposed to represent like what's going on in the world. How should I think about factors in general, or partitions? I can think about as questions. These factors in B, how should I think about those?
Yeah, I think I didn't explicitly say, but the elements of B we'll call factors. We use the word factor for the elements of B. So I almost want to say the factors are kind of a preferred basis for, yeah, the factors kind of form a preferred basis for your set of possibilities. And so, like, if I consider the set of all bit strings of length 5, right, there are 32 elements there. And if I wanted to specify an element, I can do so in lots of different ways. But there's something intuitive about this choice of breaking my 32 elements into what's the first bit, what's the second bit, what's the third bit, what's the fourth bit, what's the fifth bit. So it's kind of it's a set of questions that I can ask about my element that uniquely specify that what element it is, and also for any way of answering the questions, there's going to be some element that works with those answers. And so factorization is kind of just like it's a combinatorial thing that could be used for many different things. But one way to think about it is kind of you're making a choice that is a preferred basis, a preferred set of variables to break things up into. And you're thinking of those as kind of primitive, and then other things is built up from that. So properties like do the first two bits match is then thought of as built up from what is the first bit and what is the second bit. And so it's kind of a choice of what comes first, a choice of what are the primitive variables in your structure.
Okay. So if I'm trying to think about maybe some kind of decision problem where, I'm going to do something and then you're going to do something and then another thing's going to happen. And I want to model like that whole situation with a finite factored set. Instead of thinking about modeling like which thing is going to happen to me today, if I want to model an evolving situation, how should I think about what the set S is and what the factors should be?
Yeah. So factorization is very general, and I use the word factorization in multiple different contexts when talking about this kind of thing. But the question that you're asking, to say some more background stuff. I'm going to kind of introduce this theory of time that has a background structure that looks like a factored set rather than a background structure that looks like a DAG, looks like a directed acyclic graph, like in the Pearlian case. And so specifically, if I'm using a factored set and I am using that to interpret, or I'm using that to kind of describe some causal situation, I am not going to have nodes. I'm not going to have factors that kind of correspond to the nodes that you would have in the Pearlian world. Instead, I am mostly going to be thinking of the factors as independent sources of randomness. I'm hesitant there because a lot of my favorite parts of the framework aren't really about probability. But if I'm thinking about it in a like temporal inference setting where I'm like getting a statistical distribution of where I'm getting a statistical distribution, then I'm thinking of the factors as basically independent sources of randomness. And so if like we have some variable x and then we have some later variable y that can take on some values and partially is going to be a function of x, then we won't have a factor for x and a factor for y. We'll have a factor for maybe that which kind of goes into what x is, And then we'll have another factor that's like the extra randomness that went into the computation of y once you already knew x. And when we think of factored sets as related to probability, we're actually going to always want our factors to be independent. And so the factors can't really be put on things like x and y when there's a causal relationship between x and y.
So it almost sounds like the factors are supposed to be these like somehow initial data, like the problem setup or something, like the specification of like what's going on, but like kind of an initial specification.
Yeah, and indeed, if you like take my theory of time, so I'm gonna have like a way of taking a factored set and taking an arbitrary partition on your set S, and then I'm going to be able to like specify time, specify when some partitions are before or after other partitions. The factors will be partitions with the property that you can't have anything else that's strictly before it besides deterministic things. And so there's a sense in which like the factors are initial. Yeah, the factors are like basically kind of the initial things in like the notion of time that I want to create out of factored sets. But also intuitively, it feels like they're initial. It feels like they're like the primitive things that came first, and then everything else was kind of built out of them.
Yeah, maybe primitive is a better word than initial.
Yeah, I mean they're in the like poset of divisibility, right? I kind of want to say that like one is initial, not the primes, but like the primes have the property that like you can't really have anything else before them. Yeah, no, primitive is like prime is yeah.
Yeah. So in the sense that like when you're dividing numbers, like whole numbers, you get to primes and then you get nowhere else, and they're primitive in that sense.
Right.
Yeah. So you talk about the history of variables as like all the initial factors that you need to kind of specify what a variable is, and then you have this definition of orthogonality, and people can read the paper. I don't know if they'll be able to read a paper by the time this goes live, but they'll be able to read something to learn about what orthogonality is.
Yeah, the talk and the transcript of the talk that, for example, appears on the Mary blog or on Less Wrong, it has all of the statements of everything that I find important. And so, like, you shouldn't have to like wait for a paper. I think that like modulo the fact that you'd have to prove things yourself, it like has all of the important stuff.
So people, I think for me at least, it's easy to like read the definition of orthogonality and still not really know like how to think about it, right? So what should I like? Yeah, how should people think about what's orthogonal?
So in the like temporal inference thing, where we're going to like be connecting up these combinatorial structures with probability distributions, orthogonality just it's going to be equivalent to independence. And so one way to think of orthogonality is it is I kind of like took out a combinatorial fragment of independence where I'm not like actually working with probabilities, but I am kind of working with a thing that kind of is representing independence. Another way to think of it is like when two partitions are orthogonal, you should expect that like if you come in and tweak one of them, it will have no effect on the other one. They're kind of they're separated. And in the yeah, and in like specifically in the factored set framework, orthogonality means they do not have a common factor. And so where like these factors can be thought of as like sources of randomness or sources of something. If they do not share a common factor, then they're in some sense separated.
Yeah. So I'll just say one example that kind of helps me understand it is like this XY plane example where the factors were like what's your, you're partitioning up according to the X coordinate, and you can also partition up according to what the Y coordinate is. So you can have one different partition that's like, are you on the left hand side or the right hand side of the Y axis? That's a way to partition up the plane. It's like a variable. It's like, are you on the left or are you on the right? And there's a second variable that's like, are you above the x-axis or are you below the x-axis? Right. That also partitions the plane up. And like those two, my understanding is that in this factored set, like those two partitions, or you could think of them as variables, are orthogonal. And that kind of hopefully gives people a sense. It's also kind of nice because they're like literally, like if you think about the dividing lines, they're literally orthogonal in that case. And that's like maybe not a coincidence.
Yeah, so historically when I was like developing factored set stuff, I was actually working with things that looked like I have two partitions, and there's something nice when it's the case that they're both kind of mutually or sorry, for any way of like choosing a value of this X partition and also choosing a value of the Y partition, those two parts will kind of intersect. So in your example, right, the point is that like all four quadrants kind of exist, and this is kind of like there's a sense in which this is saying that like the two partitions aren't really like stepping on each other's toes. If we like specify the value of this X partition, it doesn't stop us from doing whatever we want in terms of specifying the value of the Y partition. And largely orthogonality is kind of a step more than that, where like a consequence of being orthogonal is that they're not going to step on each other's toes. But I have this extra thing, which is kind of like it's not. There's this extra thing, which is really just like the structure of the factorization. But there's this extra thing beyond just not stepping on each other's toes, which is coming from some sort of theory of intervention or something. Like you can view the factored set as kind of a theory of intervention because a factored set basically allows you to take your set and view its elements like tuples. And when your elements are like tuples, you can imagine kind of going in and changing one value and not the others. And so orthogonality kind of looks like it's not just X and Y are compatible, like compatible in all ways of assigning values to each of them, but it's also when you mess with one, it doesn't really change the other.
Cool. So another thing, yeah, another question about orthogonality. So in the talk that listeners can watch or read a transcript of, you sort of say, okay, we have this definition of orthogonality and this definition of conditional orthogonality, which is like a little bit more complicated but kind of similar. You then talk about sort of inference in the real world. So like we sort of imagine that you're observing things that are roughly like you don't observe the underlying set, but you observe things that are roughly like these factors. And somehow you get evidence about like what things are orthogonal to each other. And from that you go on and infer a whole bunch of stuff, or you can sometimes. And you sort of give an example of like how that might work. How would I go about gathering this like orthogonality data of like what things in the world are orthogonal to what other things?
So the default is definitely passing through this thing I call a fundamental theorem, which is saying basically that orthogonality. So the fundamental theorem says that conditional orthogonality is equivalent to for all probability distributions that you can put on your factored set, which sort of respect the factorization, your variables are conditionally independent. And so, because of this, I don't know. I phrase that as for all probability distributions, but you can kind of quickly jump that to like for a probability distribution general position. And so, the basic thing to do is if you have like access to a distribution over the things over like the elements of your set or over something that's a function of the elements of your set. If you have access to a distribution, it's kind of a reasonable assumption to say that if you have like a lot of data and it looks like these two variables are independent, then you kind of assume that they're orthogonal in whatever underlying structure produced that distribution. And if they're not independent, then you assume they're not orthogonal. And it's just like the default way to get these things is via taking some distribution, which could be coming from a bunch of samples, or it could be like a Bayesian distribution. But I think that like orthogonality is something that you can basically observe through its connection to independence versus time is not as much.
I guess this works when my probability distribution has this form where the original factors in your set B, like the primitive variables, have to be independent in your probability distribution. And if they're independent in that distribution, then conditional independence is conditional orthogonality. How would I know if my distribution had that nice structure?
I mean, you can just try to like you can just interpret all of the independence as orthogonality and see whether it kind of like contradicts itself, right? It's like you might have a distribution that kind of can't really be well described using this thing. And one thing you might do is you might kind of develop an orthogonality database where you kind of keep track of all of the orthogonalities that you observed. And then you notice that there's some orthogonalities that you observed that are incompatible with kind of coming from something like this. Yeah, I'm not sure I fully understand the question.
I guess what I'm asking is imagine I'm in a situation, right? And like I don't already have the whole finite factored set structure of the world. Like, I'm wondering how I go about getting it, especially if the world is supposed to be like my life or something, so I don't get like tons of free runs. Maybe this isn't like what it's supposed to do.
I feel like this is basically the answer you'd give here is similar to the answer you'd give to like the same question about Pearlian causality. And I think that like largely the temporal inference story makes the most sense in a context that's very like you have a repeated trial that you can repeat an obnoxious number of times, and then you kind of develop, you can get a bunch of data, and then you're trying to like tell a story about this trial that you repeated. And yeah, so the story that I tell kind of makes the most sense in a situation that's like that. I'm excited for a lot of things about factored sets that are not about just like doing temporal inference from a probability distribution, and those feel like they play a lot more nicely with like sorry, the applications that feel like they're about embedded agents to me are kind of different from the applications that feel like it's about temporal inference. It's like because it feels like you kind of need something like this, like frequentist, like lots of repetition to be able to get distribution in order to be able to like do a lot of stuff with temporal inference, or at least doing it the naive way. Maybe you can build up more stuff.
So embedded agency is your term for something like being an agent in a world where like your thinking processes are just like part of the physical world and like can be modified and modeled and such. Is that a fair summary?
Yeah.
Okay. So the applications of the kind of finite factored set framework to embedded agency, are you thinking of that more as like a way to model things?
Yeah, I'm thinking of it mostly like basically there's a lot of ways in which you want to model, like there's a lot of ways in which people model agents using graphs where the edges in the graph represent like information flow or causal flow or something that all kind of feel like they're entangled with like this Pearlian causality story. And often I think that pictures like this fail to be able to handle abstraction correctly, right? I have like a node that kind of represents my agent, and then I have like I don't really have room for another node that represents like a coarser version of my agent, because if I did, like which one gets the arrow out of it and such. Um, and so largely my hope in embedded agency is just all the places where we want to draw graphs. Instead, maybe we can draw a factored set, and this will allow things to play more nicely with abstraction. And playing nicely with abstraction feels like a major bottleneck for embedded agency.
Okay. Yeah, I'll ask more about that a bit later. Yeah, so I guess I want to ask more questions about like the kind of finite factored set concept itself. Why is it important that it's finite?
So I can give an example where you should not expect the fundamental theorem to hold in the cases where it's infinite. So the thing where independence exactly corresponds to orthogonality, in the infinite case, one shouldn't expect that to hold. And it might be that you can save it by saying, well, now we can't take arbitrary partitions. We can only take partitions that have a certain shape.
Sort of like measurability criteria.
Sort of like measurability criteria, but measurability is actually not going to suffice for this. I can give an example. Yeah, I'll just to give an example. If you imagine the infinite factored set that is countable bit strings.
So this is just like infinite sequences of ones and zeros,
Yeah,
and it's a set of all of them.
yeah. So you have the set of all infinite sequences of ones and zeros, and you have kind of the obvious factorization on this set, which is you have one factor for each bit. And then there's a partition that is asking, is the infinite bit string the all zero string? And there's a partition that's asking, is the infinite bit string the all one string? These are two partitions. Let's call them X and Y.
Okay.
And it turns out that for any probability distribution, you can put on this factored set that kind of respects the factorization. At least one of these partitions is going to have to be like, either it's going to be the case that the all zero string is probability zero, or the all one string is probability zero,
Yep.
because all of the bits have to be independent. And then you'd be able to conclude that the question, is it the all zero string and is it the all one string? Like those two questions will have to be independent in all distributions on the structure, but it really doesn't make sense to call them orthogonal.
Why doesn't it?
Why doesn't it make sense to call them orthogonal? Because it doesn't make sense to call them orthogonal because like all of our factors kind of go into the computation of that fact. And so you kind of like, if you're thinking of orthogonality as like they can kind of be computed using disjoint collections of factors. You can't really compute whether something's the all zero string or whether something's the all one string without like seeing all of the factors. I mean, you can compute it because the first time you see a one, you can say, all right, I'll stop looking. But in my framework, it's that kind of doesn't count. You have to specify upfront all of the bits you're going to use. And so I don't know. I think there's some hope to being able to like save all of this, and I haven't done that yet. And there's another obstacle to infinity, which is even the notion of thinking about the history of a partition, that's not even going to be well defined in the infinite case.
Okay, and so the history of a partition, in the finite case, it was just like the small set of factors that like determined like, well, like if I have a partition with elements like x1 through xk or something, like the history of a partition is just all of the like basic factors, all the things in my set B, where if I know like which, if you think of the things in the set B as variables, if I know like the value for all of the variables, it's like the small set of variables, such that if I know the value for all of them, I can tell the value, I can tell what partition element I'm in for the thing that I'm looking for the history of. So it's like the smallest set of like the smallest amount of like initial information or something that's like specifying the thing I'm interested in. Is that what a history is?
Yeah, that's right.
And it's a bit worrisome because usually like there's not a smallest set of sets of right, like that's not obviously well defined.
Yeah, so smallest is specifically smallest in the subset ordering. And so the history of a partition is a set of factors. And if you take any set of factors that would be sufficient to determine the value of that partition, the answer to that question, what part it's in. If you took any set of factors that were sufficient to compute the value of x, then necessarily that set of factors must be a superset of the history. And so it's not like smallest by cardinality, it's smallest by the subset ordering. And showing that this is well defined involves basically just showing that sets of factors that are sufficient to determine the value of x are closed under intersection. So if I have two different sets of factors and it's possible to compute the value of x with either of those sets of factors, then it's possible to compute the value of x using their intersection. But actually, this is only true for finite intersections. And so if I have a partition and you're able to compute the value from either of these two sets of factors, then you're able to compute the value from their intersection. But if I have an infinite class of things, then I can't necessarily compute the value from their intersection. To see an example of this, if you again look at infinite bit strings with the obvious factorization, and you look at the partition, are there finitely many ones? If you take any infinite tail of your bit string, that's sufficient to determine are there finitely many ones. But if you take the intersection of all of these infinite tails, you get the empty set.
Yeah. So one way I'm now thinking of this is like kind of the problem with infinite sets is that like they have these things that are kind of analogous to tail events or something in normal probability theory, where you depend on like all of these infinite number of things and sort of the limit of it, but the limit is actually zero, but you can't exactly.
Yeah, there's this actually what I think is a coincidence.
Okay.
But you could do this naive thing where you say, well, just take the intersection and call that the history. And then the history of the question, are there finitely many ones, would then be the empty set. And then a lot of properties would break. But an interesting coincidence here or something, I don't think it's a coincidence, but I don't like this definition. I don't like the definition of generalize things to the infinite case by just defining the history to be the intersection. But if you were to do that, then you would get that the question, are there finitely many ones, is orthogonal to itself because it has empty history. And what kind of partitions are orthogonal to themselves? They're deterministic ones, where one of the parts has probability 1 and all the others have probability 0. And the Kolmogorov 0-1 law says that properties like the question, are there finitely many ones, if all of the individual things are independent, are necessarily probability 0 or 1. And so there's this thing where if you define history in this way, if you naively like extend history to the infinite case by just taking the intersection, even though it's not closed under intersection, you actually get something that kind of feels like it gives the right answer because of the Kolmogorov 0-1 law.
Yeah, but it's going through some weird steps to get the right answer.
Yeah.
By the way, if listeners, I don't know, there are a variety of these things called 0-1 laws in probability theory, and if listeners want to think about like knowledge and changing over time, I don't know, some of these 0-1 laws are kind of fun to mull over and like think about how they apply to your life or something. I don't know, do you have comments on that claim?
No, I think Kolmogorov 0. I think that I think 0-1 law is really interesting, and I would recommend it to people who like interesting things.
All right. So back on the finite factored sets, they're sort of a way of modeling like some types of worlds, or some sorts of ways the world can be. Kind of. Are there any like worlds that can't be modeled by finite factored sets?
Yeah.
I guess infinite ones, but ignoring that for a second.
So there's this issue that's similar to an issue in Perl, where we kind of like when you look at distributions that are coming from a finite factored set or from a DAG, we're kind of looking at probabilities in general position, and so it doesn't really make sense to like have a probability 1/2 or 1/4. Although,
What do you mean by probability in general position?
so in both like my world and Pearl's world, we want to like specify a structure,
Yep.
and then we have all of the probability distributions that are compatible with that structure. And these kind of like give you like a manifold or something of different probability distributions. And then some like measure zero subset of them have special coincidences. And when I say in general position, I mean you don't have any of those special coincidences. And so an example of a special coincidence is anytime you have a probability of 1/2 or 1/4 or something like that. That's kind of a special coincidence. But to a Bayesian, that might happen because of like principle of indifference or something. Or like to like a limited Bayesian that kind of doesn't really know what, like it feels like principle of indifference kind of advises having probabilities that are rational numbers. But probabilities that are rational numbers kind of lead to coincidences in independence that don't arise from orthogonality. And so there's a sense in which my framework and the Pearlian framework kind of don't believe in rational probabilities as something that just like happens or something.
Yeah. I mean, it's even more concerning because if I think that I'm a computer and I think I assign probabilities to things, well, the probabilities I assign will be like probabilities that they're like there'll be numbers that are the output of some computation, and there are sort of a countably infinite number of computations, but there are an uncountably infinite number of like real values. So somehow like if I'm only looking at things in general position, I'm ruling out like all of the things that I actually could ever output.
Yeah. So I have a little bit of a fragment of where I want to go with trying to figure out how to deal with the fact that kind of my system and Pearl's system don't believe in rational probabilities, which is to define something, and this is like going to be informal. Well, it'll be formal but wrong. To define something that's like you take a structure that is a factored set together with a group of symmetries on the factored set that allows you to like maybe swap two of the parts within a partition, or swap two of the partitions with each other, or swap two of the factors with each other, right? And so you can have some symmetry rules. So if you, for example, considered like bit strings of length 5 again, you could imagine a factored set that it separates into the 5-bit locations, is this bit 0 or 1, but then it also has the symmetry of you can swap any of the digits with each other. I could also do swapping 0 with 1, but for now I'll just think about swapping any of the digits with each other. And then it's like subject to the structure that is this factored set and this swapping rule, or this group of symmetries, then the set of distributions that are kind of compatible with that structure will not be just things in which the bits are independent from each other. It'll be kind of any distribution in which the bits are IID, so independent and also identical. And so you could do this. You could say, well, my model of what might happen, like my like the thing that I'm going to try to infer from my probability distribution is a factored set together with a group of symmetries on that factored set. And I mean, you're not going to, at least naively, get the fundamental theorem the same way. And so I'm not sure what happens if you try to do inference on something like this. But if you want to like allow for things like rational probabilities, then maybe something like that would be helpful.
All right. So I'd like to ask a question about kind of the form of the framework. So when I think of like models of causality or of time, the two prior ones that I think of are like we talked about, Pearl's work on like directed acyclic graphs and like do operators and such, where you can just sort of draw a graph, and also Einstein's work on special and general relativity, where you have this space-time thing that's like very geometric, very curved, and like you have this time direction which is special and kind of different from like the spatial directions. Those were all like really geometric and included some nice pictures. Finite factored sets does not have many pictures. Why not? I really liked pictures.
Yeah, I mean, I think it has something to do with the variable non-realism, where it's like it feels like the points or nodes in your pictures or something. Yeah, if I take a Pearlian DAG and I'm like there are like 10 nodes in it, and even if I assume that they're all just like binary facts, then now I have, well, you take 1024 different ways that the world can be, and then you take Bell number of 1024 different possible variables that I can define on this, which is obnoxiously huge. And then there's not as much of a useful interpretation of like the arrows that connect them up or something. It's something to do with variable non-realism, where there's a sense in which Perl is kind of starting from a collection of variables, which is a way to factor the world into some small object. And because I'm like not starting with that, my world is kind of a lot larger. I don't know. Another thing that I'd like call a theory of time is people like talk about like time with like entropy. That's another example that doesn't feel as visual.
Yeah, that's true.
And I think that that's a lot more variable free, and that's maybe part of why.
Yeah, it's also the case that once you have variables, they have these like relations in terms of their histories and such, and you could draw them in a DAG or something.
Yeah, it's like the structure of an underlying finite factored set is like very trivial or something. It's like Perl has a DAG, and if you wanted to draw a finite factored set as a DAG, it would just be a bunch of nodes that are not connected at all, that each have their own independent sources of randomness. And then if you wanted to, you could maybe like draw an arrow from these nodes to all the different things that you could compute using them. Or if you wanted to say, oh, let's just have the basic variables, then it's just these nodes.
Yeah, but I guess somehow if you want to like talk about the structure that lets you talk about variables, but you don't want to talk about variables, I guess that's like less amenable to pictures, perhaps.
Yeah. I mean, I don't feel like physics and Perl have pictures for necessarily the exact same reason or something. And I'm kind of just like graphs got lucky in the way that they're easy to visualize or something like that.
Yeah, that might be right. It's also true that graphs are not like simple graphs are easy to visualize, but there are a lot of non-planar graphs that are kind of a pain to draw. Yeah, so a related question complaint I have is a lot of this work seems like it could be category theory.
Yep, it could be category theory.
Yeah, so partitions are basically like functions from a set to a different set, and like the parts are just like all the things that have the same value of the function.
Yeah, partitions is kind of like the information content of a function out that you get by kind of ignoring the target and only looking at the source,
Yeah,
kind of.
and I don't know, it seems like there are probably nice definitions of like factors and such and category. There's lots of duality, and category theory has pictures. It's also a little bit nice in that like I have to admit, looking at sets of sets of sets of sets can be a little bit confusing and after a while in a way that categories could have some nice language for that. So why isn't everything category theory, even though category theory is objectively great?
Yeah, I mean, it goes further than that. I actually like know most of the category theory story, and I've like worked out a lot of it, and kind of went with the combinatorialist aesthetic with the presentation anyway. So yeah, what are my reasons? One reason is because I kind of trust my category theory taste less, and I kept on like changing things or something in a way that I was like not getting stuff done in terms of actually getting the product out or something by working in category theory. And so it's kind of like, oh yeah, I'll punt that to the future. Another reason is because it feels like the system just like really doesn't have prerequisites. And by phrasing everything in terms of category theory, you're kind of adding artificial prerequisites that maybe make the thing prettier, but like you actually like you know what a set is, you can kind of go through the all the proofs or something. That's not entirely true, but like it's like because I'm like working in a system that has very few prerequisites, the extra cost of prerequisites is higher. Like the marginal cost of adding prerequisites is higher. Another reason was I was just really shocked by the sequence that counts the number of factorizations not showing up on OEIS. So, yeah, if you take an n element set and you count how many factorizations there are on the n element set, you get a sequence, and there's this online encyclopedia of integer sequences that has like 300,000 sequences, and it does not have this sequence in spite of having a bunch of lower quality sequences. um, and I was very surprised by this fact, and like it feels like a very like objective test. I'm not a particularly scholarly person. It's hard for me to figure out what people have already done, and I was just pretty blown away by the fact that this thing didn't show up on OEIS. And so like I kind of stuck with the combinatorialist thing because it had that objective thing for the purpose of being able to like do like an initial cell or something.
Okay.
Yeah, those are most of my reasons. I think that I haven't worked out all the category theory, but I think it will end up being pretty nice. In fact, I think that just like even the definition of conditional orthogonality, I think can be made to look relatively nice categorically, and it's via a path that is pretty unclear from like the definition they give in the talk or the posts. But there's an alternative definition that kind of looks like if you want to do orthogonality and you want a condition on some fact about the world, the first thing you do is you take your original factored set and you kind of take the minimal flattening of it so that the thing you want to condition on is kind of rectangular in your factored set. And then where by flattening, I mean you merge some of the factors together.
Okay.
And if you take the minimal factoring and then you ask whether your partitions are orthogonal in the minimal factoring, that corresponds to conditional orthogonality. And so I think that categorically there's a nice definition here. But I definitely agree about the category theory aesthetic, and I think that it actually is a good direction to go here that I may or may not try to do myself. But if somebody was super interested in trying to convert everything to category theory, I could talk to them about it.
So speaking of that, I'm wondering like what follow-up work are you excited about being done here? And do you think that like this kind of development is going to look more like kind of showing nice things within this framework? Like making it categorical, or like having a new like showing the decidability of inference like it in finite factored sets? Or do you think it's going to look more like iterating on some of the definitions and like tweaking the framework a little bit until it's like the right framework?
Yeah, I mean, the category theory thing a little bit does fall into tweaking the framework until it's the right framework, although it's a little different. I have applications I'm excited about in both spaces. Yeah, like if I were to list applications that I expect that I'm not personally going to do that like seem like projects that would be interesting for people to pick up, one of them would be converting everything to category theory. One of them would be figuring out all the infinite case stuff and looking at applications to physics. I think that there's a non-trivial chance of some pretty good applications to physics that would come out of figuring out all the infinite case stuff, because I think that factored sets are actually a lot closer to being able to give you something like continuous time than the Pearlian stuff. Yeah, so one would be the physics thing. One would be the basically trying to do computational stuff in terms of I kind of just have some like a couple like proofs of concept of how to do temporal inference, and like I think you said showing decidability of temporal inference is a thing, but really it's like being like I think that somebody should be able to like actually search over the space of like a space of a certain flavor of proof and be able to actually come up with examples of temporal inference that come from this, where you take in some orthogonality data and are able to infer time from them. And I think that there's a computational question here that I think I might be wrong, might be able to at least be able to like produce some like good examples, even if it's not like actually doing temporal inference in practice. And so I'd be excited about something like that. I would be excited about somebody trying to extend to symmetric finite factored sets, which is the thing I was talking about earlier about dealing with rational probabilities. I think that of these that I listed, the one that I'm most likely to want to try to work on myself is the symmetric factored sets thing, because I think that could actually have applications to the kind of embedded agency type stuff I'd want to work with. But for the most part, I'm expecting to myself think in terms of applications as opposed to think in terms of extending the theory. And all the things that I kind of said were all forms of extending the theory, either by tweaking stuff or by kind of putting stuff on top of it. I think it's mostly just like putting stuff on top of it. I think that like I don't say that much. Sorry, I think there aren't that many like knobs to twiddle with like the basic thing. Like you could have some like new orientation on it, but I think it'll be like basically the exact same thing. I think that the part like the way that I defined it, there's only one factorization on a zero element set. Maybe it would be nicer if there were infinitely many factorizations on zero element. Like the definitions might be slightly different, but like I think it's basically the same core thing. I think that I'm mostly thinking that the baseline I have is kind of correct enough for the kind of thing that I want to do with it that I don't expect it to be like a whole new thing. I expect it to be like built on top, and there's different levels of built on top.
So I guess I'd now like to pivot into a bit of a more general discussion about your research and your research taste. How do you see the work on finite factored sets as contributing to reducing existential risk from artificial intelligence, if you see it as doing that?
I think that a lot of it factors through trying to become less confused about agency and embedded agency, which I don't know. I have opinions in both directions about the usefulness of this. Like sometimes I'm feeling like, yeah, this isn't going to be useful and I should do something else. And then sometimes I'm like just interacting with questions that are a lot more direct and noticing how a lot of the kind of questions that I'm trying to figure out for embedded agency actually feel like bottlenecks to be able to say smart things about things that feel more direct.
Can you give an example of that?
I don't know, like Evan says some things about myopia, talks about myopia,
The seven cubinger.
right? And like that feels like a lot more direct, like trying to like get a system that's like kind of optimizing locally and not like looking far ahead and stuff like that. And I feel like in wanting to like think about what this even means, I notice myself wanting to have a better notion of time and better notion of things about like the boundaries between agent and environment and all of this stuff. And so I'm like, I don't know. That's an example of like something that feels kind of more direct. Like myopia feels like something that could be very useful if like could be like implemented correctly and could be like understood correctly. And I when I like try to think about things that are more direct than embedded agency, I feel like I hit the same kind of cruxes, and that working with an embedded agency feels like it's more directed at the cruxes, even though it's less directed at the actual application of the thing
Okay.
in a way that I expect to be useful.
What's well, like in the myopia example, I think like yeah, the first pass solution would be like, look, there's just like physical time basically exists, and we're just gonna say, okay, I want like an AI system. I want it to care about like what's gonna happen in the next 10 seconds of physical time, and not things that don't happen within the next 10 seconds of physical time. Do you think that's unsatisfactory?
Yeah, so I mean, I think that you can't really like look at a system and try to figure out whether it's optimizing for the next 10 seconds or not. And I think that like yeah, the answer that I actually gave with the myopia thing was a little off because I was actually remembering a thought about myopia, but it wasn't about time. It was about just like time was the thing that I said in that thing. It was more about like counterfactuals and more about like the boundary between where the agent is or something like that. But I don't know. I still think the example works. I mean, I think that it comes down to you want to be able to like look at a system and try to figure out what it's optimizing for. And if you have the ability to do that, you can check whether it's optimizing for the next 10 seconds. But in general, you don't really have the ability to do that, like figure out like what it's trying to do or something like that. And I think that, yeah, how do I get at the applications? Okay, so one thing I think is that in trying to figure out how the system works, it is useful to try to like understand what concepts it's using, stuff like this. And I think that the strongest case I can kind of make of factored sets is that I think that there's a sense in which factored sets is like also a theory of kind of conceptual inference. And like I think that this can be helpful for like looking at systems and trying to like do oversight of systems that you want to be able to look at a thing and figure out what it's optimizing for.
In what ways would you say it's a theory of conceptual inference?
One way to look at like the diff between like factored sets and Perl is that we're kind of not starting from a world factored into variables. Instead, we're inferring the variables ourselves. And so there's a sense in which if you try to do like Pearlian style analysis on a collection of variables, but you messed it up, and instead of having like a variable for what number this like I have a number and it's either 0 or 1, and it's also either blue or green. And I can also invent this concept called GRU, which is a green 0 or a blue 1. And instead of thinking in terms of like what's the number and is it blue, you can think of what's the number and is it GRU. And maybe if you're like working in the latter framework, like you're kind of using the wrong concepts and you will not be able to kind of pull out all the useful stuff you'd be able to if you were using the right concepts. And factored sets kind of has a proof of concept towards being able to distinguish between blue and GRU here, where the point is that in this situation, if the number is kind of independent of the color and you're working with the concept of number and the concept of GRU-ness, you have this weird thing where it looks like there's a connection between number and GRU-ness, but it also is the case that if I kind of invent the concept of number XOR GRU-ness, I kind of invent color, and color lets me like factor the situation more and see that maybe you should think of it as like the number and the color are primitive properties, like we were saying before, and GRU-ness is like a derived property. And so there's a sense in which like earlier things are more primitive, and it's not just earlier things. I think there's more than just that, but there's a sense in which like because I'm not taking my variables or my concepts as given, I'm also doing some like inferring which concepts are good.
So somehow, yeah, I guess this. Yeah, it strikes me that like inferring which concepts are good is a related but different problem to inferring which concepts a system is using.
I don't know, like there's stuff that you like to think about that involve like kind of having like separate neurons as part of it. And I think there's a sense in which like it might be that we're confused when we're like looking at a neural net because we're thinking of the neurons as like more independent things when really they could be like a transform similar to the blue GRU thing from some other thing that is actually happening, and being able to have like objective notions of what's going on there, like being able to like have a computation and have it like having there be a preferred basis that like causes things to be able to factor more or something feels, yeah. So I guess I'm concretely pointing at the picture of like factorization into neurons in the result of a learned system might be similar to GRU.
Yeah, it's interesting in that like people have definitely thought about this problem, but like the all the like work on it seems kind of hacky to me. So for instance, like so I know Chris Ola and collaborators now or formerly at OpenAI have done a lot of stuff on using like non-negative matrix factorization to kind of get out the like linear combinations of neurons that they think are important. And like the reason they use non-negative matrix factorization, as far as I might be getting this wrong, but as far as I can tell, it's because it kind of gets good results, sort of, rather than like a theory of like non-negativity or something. Or like a similar thing is there's some work about trying to figure out whether like the concepts in neural networks are like on the neurons or whether they're like these linear combinations of neurons. But the way they do it, which again, I don't know, I'm going to sound critical here, is like a good first pass. But a lot of this work is like, okay, we're going to make a list of all of the concepts, and now we're going to test if a neuron has like one of the concepts which I've decided really exists. And we're going to check random combinations of neurons and see if they have concepts which I've decided exist, and which does better. Yeah, there's definitely something unsatisfying about this. Maybe I'm not aware of more satisfying work. Yeah, it does seem like there's some problem there.
And again, I think that like you're not going to be like directly applying the kind of math that I'm doing, but it feels like I kind of have like a proof of concept for how one might be able to think of blueness as a statistical property. Like blueness versus GRU-ness as like a statistical property is something that you can kind of get from raw data. And like, I don't know, I feel like there's a lot of hope in something like that. But that's also like not my main motivation. That was like a side effect of trying to do like the embedded agency stuff. But it's kind of not a side effect because I think that like the fact that I'm like trying to do a bunch of embedded agency stuff, and then I was trying to like figure out stuff related to time and related to like decision theory and agents modeling themselves and each other. And like I feel like I stumbled into something that might be useful for like identifying good concepts like blue. And I think that stumbling is part of the motivation. Like I don't know, that stumbling is part of the reason why I'm thinking so abstractly, right? Like that's not a motivation for thinking about embedded agency. That's a motivation for thinking like as abstractly as I am, because like you might get far-reaching consequences out of the abstraction.
All right, so I guess a few other questions to kind of get at this. What do you do? Like, what does a day of like Scott researching look like?
I mean, recently it's been like thinking about presentation of of factored set stuff. Like often involves like thinking in overleaf or something where I'm just like writing some stuff up, and then I like have thoughts as a consequence of the writing. Often it looks like talking to people about different formalisms and different like weird philosophy. Yeah, I don't know.
So you're thinking about presentation of this work. What are you trying? What are you trying to get right or not get wrong? Like what are the problems that you're trying to solve in the presentation?
I mean, I think the large part of the presentation thing is I want to like wrap everything up so that it feels like something that can just be used without thinking about it too much or something like that. Part of the presentation is like some hope that maybe it can like have large consequences to the way that people think about structure learning, but mostly it's like kind of having it be a basic tool that I can then kind of like I've kind of like locked in some of the formalism such that I don't have to like think about these details as much and I can think about the things that are built on top of them. I don't know. Like I think that I don't know. I think that like in thinking about this presentation or something is not where like the interesting work is done. Like I think that like the interesting like the part that had like a lot of interesting meat in terms of actually how research is done was like a lot of the stuff that I did like late last year, which was kind of okay. I finally wrapped up Cartesian frames. What is it missing? And it largely was. I had this orientation that was Cartesian frames kind of feel like they're doing the wrong thing, similar to or sorry, like all right. So here's like a story that I can kind of tell, which is I was looking at Cartesian frames, which is some earlier work from last year, and part of the thing was you, you viewed this world as a binary function from like an agent's choice and an environment's choice, or like an agent's way of being or an agent's action to the environment's way of being, or sorry, cross the environment's way of being to like the full world state. And a large part of the motivation was around taking some stuff that was kind of treated as primitive and making it more derived. In particular, I was trying to make time more derived and some other things, but I was trying to like make time feel more derived so that I can kind of like do some reductionism or something. And at the end of Cartesian frames, I was unsatisfied because it felt like the binary function, like the function from a cross e to w, was itself derived but not treated that way. Like when I look at a function from a cross e to w, I don't want to think of it as a function. I want to think of it as like, well, there's this object a cross e and there's this object w, and there's like a relation between them, and then there's that relation kind of satisfies the axioms of function, which is like for each way of choosing an a cross e, there exists a w. But then I also wanted to say, well, it's not just a function from a cross e to w, where a cross e is a single object. There's this other thing, which is I have this space a cross e, and I'm specifically viewing it as a product of a and e. And what was going on there was it felt like in my function from a cross e to w, I did not just have it's a function, not a relation. I also had this like system of kind of interventions where I could imagine tweaking the a bit and tweaking the e bit independently. And the product, like a cross e as an object, a cross e, it has like the structure of a product. And I was trying to figure out what was going on there in a way that the same way that you can view the function as just a relation that satisfies some extra conditions, I wanted to view the product as some extra conditions. And those extra conditions were basically what kind of grew into me being really interested in like understanding the combinatorial notion of orthogonality. And so I was like dissatisfied with something being like not quite philosophically right or not quite derived enough or something, and I like double clicked on that a bunch.
Okay. So another question that I want to ask is, so you work at MIRI, the Machine Intelligence Research Institute. And I think among people who are trying to reduce existential risk from AI, as a shorthand, people often talk about like the MIRI way of viewing things, and the thoughts that MIRI has or something. I also work at Chai. So Chai is the Center for Human Compatible AI, and sometimes people talk about like the Chai way of doing things, and that always makes me mad because I'm an individual, damn it. How do you think if people are modeling you as like just, like one of the Mary people, like essentially like basically identical to Abram Dembski, but with like a different hairstyle. What do you think people will get wrong?
Yeah, so I've been doing a lot of like individual work recently. So it's like it's not like there's like I'm like working very tightly with a bunch of people. But there is still something to be said for like, well, even if people aren't like working tightly together, they have like similar ways of looking at things.
Maybe like in a world where they like really understand Abram and the rest of the people.
Yeah, I mean I can point at like concrete disagreements or differences in methodology or something. I think that Abram and I have some disagreements about time. Like I think that there's a thing where Abram I think Abram more than like anybody else is like taking logical induction seriously and kind of doing a bunch of work in like the field that is generated by and exemplified by logical induction. And I look at logical induction and I'm like, you're just like putting all this stuff on top of time, and I don't know what time is yet. And I need to go back and reinvent everything because it's like built on top of something, and I don't like what it's built on top of. And so I end up being like a lot more disconnected and a lot more pushing towards, I don't know, like I think that like Abram's work will tend to be more on the surface directed toward like more on the surface feel directed towards the thing that he's trying to do or something, and I will kind of just like keep going backwards into the abstract or something. I also think that like there are a lot of similarities between the way of thinking that people in Miri share and like also some large subset of people in AI safety in general, that like they're just like a bunch of people that I can kind of predictably expect if I come up with a new insight and I want to communicate it to them, it'll go kind of well and quickly, not just because they're smart, but because they're like on the same background. Like they have like the same, there's less inferential gap, but yeah, people are individuals.
It's true. Yeah. So speaking of this desire to like make things derived, like okay, where does time come from and such? What do you think you're happy to see is just like primitive?
I don't think it's a what. I think it's something like taking something that you're working with that you think is important and like doing reductionism on it is a useful tool when you have something that is both like critical, like you need to understand this thing, and there's like actual mutual information between this thing that I'm holding and stuff that I care about, and also it feels like this thing that I'm holding has all these mistakes in it or has all these like inconsistencies, right? Like it's like, why be interested in something like decision theory? Well, decisions are important, and also if you like zoom in at them and look at the edge cases, you can kind of see they're built on top of something that feels kind of hacky. And then it's like a thing that you can do is you can say, well, what are they built out of? Like what's, yeah, you can try to do some sort of reductionism. And so it's more a move for when things aren't like clicking together nicely. Like it's not like, yeah, I don't think of reductionism as like get down to the atoms. I think of reductionism as like the pieces don't fit together correctly. Go down one more step and see what's going on or something.
So a related question that is kind of, it might be too direct, but suppose a listener wants to develop an inner Scott. Like they want to be able to like, what would Scott say or think about such and such topic, just restricted to the topic of like reducing existential risk from AI. What do you think the most important opinions and patterns of thought are to get right that you haven't like already explicitly said?
So it depends on whether they want an inner Scott for predicting Scott or whether they want an inner Scott for just generally giving them useful ideas or something in space, being like a thing to bounce things off of and say, I want to like understand X more. One question is, what would Scott say about X? And it's not actually important that it matches. And it's more important, does it generate useful thoughts? Which is generally what I do with my models of people. I like have inner people, and then sometimes I find out that they don't exactly match the inner people, and I don't care the outer people, and I don't care that much because their main purpose is to give me thoughts. So I want to make it better, but it's not for prediction; it's for ideas. So I have an inner Scott, and my inner Scott is kind of a little bit being rewritten now because a large part of my inner Scott was kind of identifying with logical induction, and I actually like do this for a lot of people. I like think about their thought patterns as in relation to things that they've developed. And so, like, if I were to tell that story, I would say things like, well, like part of the thing in logical induction is that you don't make the subagents have full stories, right? Like a large part of what's going on in logical induction is it's a way of like ensembling different opinions where you don't require that each individual opinion can answer all the questions. You like allow them to specialize, and you allow them to like fail to be able to model things in some domains, and just like you want them to be able to like track what they fail to be able to model. And so I have a lot of that going on where I just like have kind of like boxed fake frameworks in my head where I'm just like very comfortable like drawing analogies to all sorts of stuff. And I don't know, I like, for example, wrote a blog post on what does the Magic the Gathering color wheel say on AI safety or something. I'm like, I do that kind of thing where I'm just like, here's a model, it's useful for me to be able to think with or something. And I'm not trusting it in these ways, but I am kind of like trusting it as being generative in certain ways. And I keep on working with it as long as it's generative. Yeah, what am I saying? I'm saying that I tend to think that if something is fruitful and like creating good ideas, but also being wrong in lots of ways, I wouldn't say don't mess with it, but if messing with it breaks it, undo that messing with it and let it be wrong and still be fruitful or something. And so I like tend to like work with obviously wrong thoughts or something like that.
Okay. Another question about like intellectual production is like there's this idea of like complements to something where like, if like complements to some production process or things that are not exactly, maybe I partially mean inputs or inputs to the process or things, separate from the process that make the process better. So in the case of like Scott Garrabrant doing research, what are the like best complements to it?
I think that isolation's been pretty good actually. Does that count? Is that a compliment? Is that the type of compliment?
I just realized that I've been kind of confused about what complement is, but it's at least an input. What's been good about isolation?
I don't know. I've just like largely been thinking by myself for the last year as opposed to like thinking with other people. And it felt like it was good for me for this year or something. I might want to go back to something else. And why? I mean, I think there is a thing where I have in the past made mistakes of the form trying to like average myself with the people around me in terms of what to think about things. And this is like dampening just because of law of large numbers, I guess.
Or it's the heat equation, right? Like everyone averages
Yeah,
everyone else, and event things become uniform.
right. There's a sense in which like working with other people is grounding in that it like keeps on getting feedback on things. But like grounding kind of, I don't know, grounding has good things and has bad things associated with it. And like one of the ways in which it's like has bad things associated with it is that like I don't know, it's like things can like flow less or something.
Yeah, it's funny. I don't exactly know what grounding is in the social sense. I recently read a good blog post about it, but I totally forgot. I mean, there is one sense in which like so if I think about literal physical grounding in electronics, like the point of that is to equalize your like electrical potential with the electrical potential of the ground, so that you don't build up this big potential difference and then have someone else like touch it and touch the ground and have some crazy thing happen. But like as long as you have the same potential as the ground, it means that there's no like net force for charges to like move from the ground to you or vice versa, but it does mean that it's like things can sort of move in both ways. And I don't know, I think maybe there's an analogy here of like if you're like something about being averaged with a bunch of people. I guess it sort of forces you to develop a like communication protocol or like common language or something that like somehow facilitates like flow like flow ideas or whatever and just directly because like your other people have ideas and you average them into you as part of like or some kind of average. Maybe literal averaging is not right. I don't know, I'm kind of blathering on. Does any of that resonate?
I'm not sure.
Okay, so we can move on. Is there anything else that I should have asked?
Yeah, I mean, I have like thoughts about, or I have like a large space of thoughts in which I don't even know what exactly I'd say next or something about like how I plan to use factored sets, I think. Because I think it actually does like differ quite a bit from like the use case in the paper slash video slash whatever blog post. That's one thing that comes to mind. Let me keep thinking for more. Yeah, I guess that's the main thing that comes to mind.
Okay, how do you plan to use it?
I mean, so one piece of my plan is that like I talk a bunch about probability, and I don't really plan on working with probability very much in the future. Like a large part of the thing is I'm kind of pulling out a combinatorial fragment of probability so that I can, or combinatorial fragment of independence, so that I can avoid thinking of things with probability or something like that. Like I don't really talk about probability in Cartesian frames, and like a lot of the stuff in Cartesian frames, I think can slash I hope to like port over to factored sets. It's largely like there are lots of places where I'd want to draw a DAG, but I'd want to never mention probability. Or maybe I could mention probability. Maybe I could think of things as sometimes being grounded in probability, sometimes not. But like, I want to draw DAGs all over the place. And I have this suspicion that, like, well, maybe places where I'm drawing DAGs, I could instead, like, think in terms of factored sets. Although, like, I have to admit, DAGs are still useful. Like I still like I have this like example where I can infer some time in factored sets that's not the one that I like given the talk. And like when I think about it, I have like a graph in my head that's like the Pearlian picture, which maybe has something to do with the fact that you're saying that like Perl can be visualized, but like it definitely feels like I haven't fully ported my head over to thinking in factored set world, which seems like a bad sign, but it also doesn't seem like that strong a bad sign because it's new.
Yeah, I mean, graphs do have this nice, like, somehow if you want to understand dependence, like, it's just so easy to say, well, like, this thing depends on this thing, which depends on these three things, and, like, it's very nice to, like, draw that as a graph, you know?
Yeah, I mean, I'm more thinking in terms of screening off. Screening off is like a nice picture when you're kind of like imagining like getting in on a path and you kind of like block the path and you kind of condition on something on the path and then like information can't flow across anymore.
Yeah, so like, a variable screens something off, like, it's, yeah, can you just say, like, what screening off means?
I mean, the way I'm using it here, I'm mostly just saying like X screens off Y from Z if Y and Z are orthogonal given X, where orthogonal could mean many different things. It could mean like thing in graphs, it could mean independence, it could mean the thing in factored sets.
But yeah, I guess, like, the idea of paths and graphs gives you this kind of nice way of thinking about screening off.
Yeah, so I do feel like I can't really picture conditional orthogonality as well as I can picture deseparation, even though I can give a definition that's like shorter than deseparation and captures a lot of things.
So yeah, speaking of Cartesian frames, so Cartesian frames is some, I guess, a framework you worked on, as you said, last year. And one thing that existed in Cartesian frames was it had this like notion of sub-agency, where like it was if you had an agent in an environment, you'd kind of talk about what it meant to view it as like somehow a collection or a composition of sub-agents. So yeah, this question we're just going to assume that listeners basically get the definition of that, and you can skip ahead to the last question if you want to look that up or don't want to bother with that. But I'm wondering, like, so these finite factored sets, it's kind of easy to see how, like the world being a product of the agent and the environment, that's kind of like this factorization thing. I'm wondering, like, how you think the notion of this subagents thing goes into it, because that was the thing I was like kind of it was kind of the most interesting part of Cartesian frames.
Yeah, so I think that I actually do have to like say something about the definition of subagent
Okay.
to answer this, which is like in Cartesian frames, I gave multiple definitions of subagent, and one of them was kind of opaque, but very short. And I kind of like justified, like, I kind of like mutually justified things. It's like, this is pointing to something you care about because it agrees with other definitions, but it's really carving it at the joints because it's so simple. So, like, it shouldn't be clear why this is a subagent, but in Cartesian frames, I had a thing that was like C is a subagent of D if every morphism from C to bot factors through D. And when you think about bot, there's a sense in which you can kind of think of bot as like the world, because bot is the thing where the agent kind of just gets to choose a world and the environment doesn't do anything. And so you can view this thing as saying every morphism from C to bot factors through D. And I think this translates pretty nicely. It's not symmetric in the Cartesian frame thing, but I think it translates pretty nicely to D screens off C from the world. C is a subagent of D means that D screens off C from the world. In the Cartesian frame thing, it's not a symmetric notion. When I convert to factored sets, it becomes a symmetric notion, and maybe there's something lossy there.
And by screening off, you mean this conditional orthogonality?
I mean conditional orthogonality. I'm saying factoring through, like saying a function factors through an object is like similar to a screening off notion. And the way that I define subagency in factored sets looks like this. So I can say more about what I say about the world. The world is like maybe some high level world model that we care about. So we have some partition of our finite factored set W, which is kind of representing stuff that we care about. And we have some partition that's maybe like, we have some partition D, which corresponds to like the super agent and like the choices made by the super agent. And we also have some partition C, which corresponds to the choices made by our subagent. And so, like, you could think of like maybe D is like a large team, and C is like one subpart of that team. And if you imagine that like the large team has this channel through which it interacts with the world, and that D kind of represents the output of the large team to the world, but then internally it has some like internal discussions. But those internal discussions never kind of leave the team's internal discussion platform or whatever. Then there's a sense in which if I know, like if the team is like a very tight team and C doesn't really have any interaction with the world besides through the official channels that are D, then if I want to know about the world, once I know about the output of D, learning more about C doesn't really help, which is saying that like C is orthogonal to the world given D.
How is that symmetric? Because normally, like, if X is orthogonal to Y given Z, it's not also the case that Y is orthogonal to Z given X, right?
Sorry, it's symmetric with respect to you're not replacing the given.
Oh, okay.
By symmetric, it's symmetric with respect to swapping. Yeah, when I said symmetric, obviously I should have meant yeah, it's symmetric with respect to swapping C with W, and D is in the middle. Which yeah, what does it mean to swap C with W?
That's kind of strange.
It's capturing something about being a subagent means that kind of the interface of the super agent is kind of screening off all of your stuff. And like one way to see this is if we weren't working with I was thinking of this in terms of like W's everything we care about, but if we weren't thinking about W's everything we care about, if we just took any partition X and any other partition Y, and we let C be equal to X, and we let D be equal to the common refinement of X and Y, then D screens off C from the world. So if you take any two choices, any two partitions, and you just put them together, you get a superagent under this definition. And you can kind of combine any partitions that are kind of representing some choices or something maybe, and you can combine them and you get superagents. But that's like superagent with respect to like the whole world, and then as you take a more restricted world, now you can have subagents that are not just one piece of many pieces, but instead maybe the subagent can have some internal thoughts that don't actually affect the world and are not captured in the superagent, which is maybe only capturing like some more external stuff.
Yeah. I guess, like, but one thing that comes to mind is that, like, yeah, so we had this weird thing where your candidate definition of a subagent you could swap out the sub-agent with the rest of the world. Because we were thinking of an agent as like a partition. Like probably not all, like just the choice of an agent maybe as partition. But probably like not all partitions, not all variables should get to count as like being an agent, right? And I'm wondering if there's like some restrictions you could place on like what counts as an agent at all that would like break that symmetry.
Yeah, you could. I don't actually have a good reason to want to here, I think. Like I think that part of what I'm trying to build up is to not have to make that choice of what counts as an agent and what doesn't. Like I don't know, I can define this subagent thing and I can define things like this partition observes this other partition. So like a embedded observation, which I haven't like explained. And I feel like it's useful that I can give these definitions and they extend to these other partitions that we don't want to think of as agentic either. I actually feel a little more confused in the factored set world about how to define agents than I did before the factored set world. Because if I'm like trying to define agency, my kind of go-to thing is like agency is time travel. It's this mechanism through which the future affects the past through the agent's modeling and optimization. And now I'm like, well, part of the point of factored sets is I was trying to actually understand the real time such that time travel doesn't make sense as much anymore. And one hope that I have for saving this definition and thinking about what is an agent in the factored set world is the factored set world leads to multiple different ways of defining time. And so just like we want to say an agent there's some sort of internal to the time, there's some sort of internal to the agent notion of time where it feels like the fact that I'm going to eat some food causes me to drive to the store or something. So like internal to the agent, there's some time, and then there's like also the time of physics. And so one way you could think of agency is where there's kind of different notions of time that disagree, and there's a hope for having a good system of different notions of time in factored sets that comes from the fact that we can just define conditional time the same way we define conditional orthogonality. We can just imagine taking a factored set, taking some condition, and now we have a new structure of time in the conditioned object, and it might disagree. And so you might be able to say something like agents will tend to have like different versions of their time disagree with each other, and this might be able to be made formal. I don't know. This is a vague hope.
All right, cool. Well, maybe that gives people ideas for how to extend this, or for work to do. So, yeah, I guess the final question I would like to ask is, yeah, if people have listened to this and they're interested in following you and your work, how should they do so?
Yeah, so specifically for finite factored sets, everything that I've put out so far is on Less Wrong. And so you could Google some combination of my name, Scott Garrabrant, and Less Wrong, and finite factored sets. And I intend for that to be true in the future. I tend to keep posting stuff on Less Wrong related to this and probably related to future stuff that I do. Yeah, I tend to have big chunks of output rarely. So I think that, yeah, I haven't posted much on Less Wrong since posting Cartesian frames. And I'm currently planning on posting a bunch more in the near future related to factored sets. And that'll all be on Less Wrong.
All right, Scott, thanks for being on the podcast. And to the listeners, I hope you join us again.
Thank you.
This episode is edited by Finn and Adamson. The financial costs of making this episode are covered by a grant from the Long Term Future Fund. To read a transcript of this episode or to learn how to support the podcast, you can visit axrp.net. That's axrp.net. Finally, if you have any feedback about this podcast, you can email me at feedback@axrp.net.